Hi everyone, my name is Vanessa Moody and today I'll be presenting on reinforcement learning for games and simulations as a part of the Deep Learning course at the Harvard Extension School. So to start with, what is reinforcement learning? There are a multitude of answers to this that I could think of. One of the first answers is that reinforcement learning is a surprisingly older field which has come back into popularity in recent years. Now there are about 40 poster presentations at NeurIPS on reinforcement learning, but it traces back to the 90s and maybe earlier. Some of the first papers that I found were from the 90s, where researchers were really starting to formalize this problem and denote it as reinforcement learning. So the more technical definition of reinforcement learning is a training framework where an agent learns to interact with an environment to optimize the accumulated reward. So the agent and the environment are intrinsically intertwined, and that is demonstrated at a very high level, at the 1,000-foot level in this figure at the bottom here. So the agent interacts with an environment by taking actions in that environment to progress the environment forward to the next state. And in response, the agent sees a state, which is really a multidimensional array of data and of potentially multimodal data from the environment. And then the agent also sees a reward, which is usually just an integer of a point value of how many points the agent receives as a result of the actions that it has taken over the trajectory in this environment. And so the agent, in more recent years, the agent is essentially a neural network or your function approximator, and it is composed of convolutional components and recurrent components, and it outputs generally a policy of how to interact with the environment, where this policy is a policy vector of probabilities over the possible actions that it could take. So for this reason, another definition of reinforcement learning is a probabilistic program or solver of a Markov decision process, where the probabilistic program is the policy that I mentioned of a vector of probabilities about how the agent could interact with the environment. So this is kind of interesting because many environments are not fully deterministic. They have stochasticity within them in the transition state, or the transition function that determines how the environment progresses forward from one state to the next. And because there's stochasticity, there also needs to be stochasticity in the agent's response. And there are also environments such as rock, paper, scissors, where it's very important for your agent to have stochasticity, because if the agent decides upon a fully deterministic policy, like always choosing rock, then it will lose every time because it's very easy to exploit, and you can easily win by always choosing paper. So for this reason, the agent comes up with a probabilistic policy about how it will interact with an environment. There are also a few other interesting components of reinforcement learning that I won't go into too much depth with, but the other interesting component here is that the agent is also charting the course that it will take through the environment, and so it's essentially choosing the training data that it sees. And so one very important parameter to look at for reinforcement learning is the exploration versus the exploitation trade-off. So at the very beginning, it's important for the agent to explore the environment to try to better understand it. And then near the end of the training round, the agent needs to start exploiting the environment or trying to achieve the maximum possible reward return. And so one way to explore the environment is to not favor one action over another, and to put out a more uniform vector of probabilities about the actions that it might take in this environment. So reinforcement learning is, another answer for what reinforcement learning is that it is a field that has many applications, from mission planning to human AI collaboration to explainable AI, so using reinforcement learning to better understand the reinforcement learning neural network by looking at the actual actions that your agent is producing in an environment, And then drug design is another field where reinforcement learning can be used, surprisingly, to essentially try to design new drugs and to provide a reward signal where drugs that have promising biological properties are going to be favored, are going to result in a larger reward return. So because reinforcement learning has so many applicabilities, another one is in automation and in moving or helping robots learn how to interact with their environments. And there's so many different applications, and as a result, it's become a really interesting and important research area in the past few years. So the second question I want to bring up is, what is AlphaStar and what is StarCraft 2? So if you've heard of AlphaStar, these are about 10 different figures that are describing AlphaStar. But AlphaStar is a reinforcement learning agent that learned to play the game of StarCraft 2 and learned how to do so at a level where it could actually beat professional players. Without going into too much depth, StarCraft 2 is a game where you have different units with different parameters, such as the hit points, the damage done, how fast they can move, and the goal, or the reward that your agent gets, is if it is able to beat the opponent that it's up against. So some of the figures on the bottom here are showing what the agent is seeing in this GIF, how the neural network is activating in response, and one of the more interesting figures is in the middle right, the figure denoted outcome prediction. And this is actually showing that as this situation progresses, the agent realized that it is actually winning this encounter, this engagement, which is a really big deal because this is against a professional player. And if you look in the upper left video, this is the agent's view, and then in the upper right is the professional player's view, and he starts trying to fall back here as he begins to lose. And meanwhile, the agent knows it's winning and it pushes its advantage. So this is just demonstrating the capabilities of reinforcement learning. And I really believe there's a lot of interesting development that will continue to be done in this area. There's a lot to be done here. So now I'll start by, I'll walk us through the tutorial of a reinforcement learning agent that I trained to play the game of StarCraft 2 and to play a much simpler mini game of StarCraft 2. So I'll go ahead and show my code review now. Great. So now I'll go ahead and walk through the code tutorial. The scope of this final project was to rewrite one of the existing code bases for a StarCraft 2 reinforcement learning agent, specifically the A2C, the Advantage Actor Critic agent, and to rewrite this code base with updated libraries. So this code base uses an older version of TensorFlow, and I decided to rewrite it in PyTorch as a resource for users that are more familiar with PyTorch and in the most updated PyTorch version. And then I also rewrote it for compatibility with the most recent PyC2 version, where PyC2 is the library that allows for StarCraft 2 API interaction. So to start with, I'll go ahead and run the system. The entry point is run.py, and one thing you can do is specify the number of environments that you want to run with. In this example, I'll specify 2 to show that now 2 StarCraft instances are going to start up at once. So here are those 2 instances. The map that you'll see is the Move to Beacon minimap, which is a very simple StarCraft minigame where the agent has to move its Marine to the green glowing beacon. And here you can see that the agent is starting to move around, and there's a slight pause after every trajectory is finished when the loss is being calculated and the agent's parameters are being updated. And I'll go ahead and kill this now and walk through the code base. So there are 3 files to be aware of in this code base. The first is the run.py file, which I just ran, and there are a few flags that might be helpful. Environments is the number of environments, and it's set to default as 1 so that your computer isn't overtaxed with 30 environments opening up at once. Some of the other helpful parameters might be the map, so you can test this out with different StarCraft minigames. The learning rate is another one that I've used for debugging, and the number of iterations, but by default it will run for infinity. I won't go into too much detail over this. Most of this came from the reinforcement learning PyC2 RL agents GitHub that I mentioned. The only modification I really had to make here was in the PyC2 environment arguments used to set up the StarCraft API. So some modifications were required here for this to interface with the most recent PyC2 version. And then in this function, the runner is started, which collects batches of trajectories to use to update the loss score. And the model is built, which is the agent. So this is akin to instantiating a PyTorch class module. So in the runner.py file, there are a few helper functions up top, but the big class is the agent runner class and the run batch method within it. And so this is basically calculating accumulated trajectories across all of the environments that are being ran at the same time, as well as the rewards and the done signal. And then it's using that, so it's feeding in the observations into the agent model, which comes up with that policy vector that I mentioned, and it also comes up with a value estimate of the environment. And this is a key parameter of A2C agents. They come up with value estimates of their environment. And then you sample an action from your probabilistic policy vector. You transform it so it's compatible with PyC2, so the data format is correct. And here we also have the computation of the loss signal. There are a few different components of the loss signal. So there's the policy loss, the value loss, and the entropy loss, which is basically a regularizer on the policy vector. And then you add them all together in the loss score and go ahead and update it by calling the backward method and the optimizer step method, as you normally do for PyTorch. And finally, I'll show the agent class here. So this is a PyTorch module, as I mentioned, but one of the interesting augmentations I had to work through here was essentially adding a build method on this class so that when the first StarCraft 2 observation is seen, then you instantiate all of your convolutional neural network dimensions and linear neural network dimensions. And that's because this StarCraft 2 environment has multimodal data of all sorts of different dimensions. There are 17 different feature screens, and there are actions that require spatial arguments of where to attack at. And so because of all of these different data formats, you essentially have to instantiate once the environment has been set up already. So the build method is doing that, and it's going ahead and setting attributes on this class according to the environmental features that are seen. So that was one of the interesting heuristics that had to be implemented here. Then the other thing to look at is the forward method, which I mentioned before, but this takes in the observation and it returns the policy and the value by passing it through those instantiated neural network components. And that's the high-level overview of the code base, and next I'll go ahead and walk through some of the preliminary results from this study. In summary, I was able to train a variety of agents during the course of this final project. This is one of the agents depicted that was not able to score highly in terms of the cumulative reward. However, there are some promising behaviors in the individual components of the loss, specifically for the policy loss, which is decreasing as it should be, and the entropy, which is increasing as it should be. When training these agents, I ran into a lot of difficulties with the additional fine-tuning required, especially between the ratios of these individual loss components used. And so a lot of different iterations of adjusting these hyperparameters is definitely required, and further research would be required to produce a performant agent. The final thing I'll note is that these agents do have interesting reward signals. This is an example of a performant agent from a different GitHub repository that actually was able to optimize its score after 5,000 epochs. So I might have been on the cusp of having a performant agent and cut off training prematurely. And that is another property which goes into training these agents. In summary, this is a really interesting and engaging opportunity. Thank you for the opportunity to do this research in reinforcement learning. I was able to learn a lot, And some of my major takeaways were that reinforcement learning is extremely difficult, but at the same time, extremely rewarding to do research into. Thank you for your time.